Massive rivers of gas are silently flowing through the cosmos. These are galactic winds, powerful streams of energy that shape the very fabric of our universe. They hold the keys to some of astronomy's greatest mysteries, from why some galaxies stop making stars to how the cosmos evolved over billions of years. By the end of this journey, you will understand the 25 crucial clues that are helping scientists unravel these cosmic secrets. We will explore how a supermassive black hole's fury can blast material clear across a galaxy, and why ancient fossilized winds still whisper their stories to our telescopes. What cosmic force do you believe is the most powerful sculptor of galaxies? The first clue emerged not from a single moment of discovery, but from a slow, dawning realization. For decades, astronomers peering at distant galaxies noticed something peculiar. The light from certain elements, like oxygen and hydrogen, was not where it was supposed to be. It was shifted, stretched, and scattered, suggesting vast amounts of gas were moving at incredible speeds, flowing outwards from the galactic core. The key was in the spectral lines, the unique fingerprints that light leaves behind. These fingerprints were smeared, telling a story of violent motion. It was as if the galaxy itself was breathing out a hurricane of material. The pivotal confirmation came with the power of new eyes in the sky, like the Hubble Space Telescope and giant ground-based observatories. They provided the sharp, detailed views needed to see these outflows not as blurry anomalies, but as structured, colossal winds. Researchers like Sylvain Velu and Timothy Heckman were among the pioneers who connected the dots, arguing that these were not minor hiccups but fundamental processes. They realized they were looking at the primary engine for galactic change, a force capable of altering a galaxy's destiny. This initial clue, the simple act of seeing the wind for the first time, opened the floodgates to a much deeper mystery. What could possibly generate such immense power? These spectral fingerprints did more than just confirm a wind was blowing. They revealed its staggering power. The shifts in light showed gases racing away from their home galaxies at speeds of millions of miles per hour. This was not a gentle breeze, it was a torrent, a cosmic hurricane capable of sweeping entire star systems clean of the raw materials needed for new stars. But what cosmic engine could possibly achieve this? The first suspects were the most violent events astronomers knew. On one hand, there were starburst galaxies, regions where stars were being born in a frantic, explosive frenzy. In these stellar nurseries, the most massive stars live fast and die young, exploding as supernovae. Theorists proposed that the combined fury of thousands of these supernova explosions could act like a piston, driving a powerful wind outwards from the galaxy's disk. It was a compelling idea, a feedback loop where star birth itself triggered a wind that would eventually shut down future star birth. Yet there was another, even more formidable suspect. At the heart of nearly every large galaxy lies a supermassive black hole. When these monsters feed, the material swirling into them heats up to incredible temperatures, blazing with radiation. This creates an active galactic nucleus, a beacon of energy so intense it can outshine the entire rest of the galaxy. Could this be the ultimate power source? Early models suggested that the intense radiation pressure from an active nucleus could push against surrounding gas, accelerating it out into the void. So, which was it? Was it the collective death of stars or the ferocious appetite of a black hole? For a long time, it seemed like it had to be one or the other. This was the central puzzle, a cosmic whodunit where the fate of galaxies hung in the balance. The answer to this cosmic power struggle was written in the wind itself. We just had to learn how to read its chemical language. The second clue came not from the speed of the gas, but from its very substance. What were these galactic hurricanes actually made of? By breaking down the light from these outflows into its constituent colors, astronomers could identify the specific elements present, creating a detailed chemical fingerprint for each wind. These fingerprints told a dramatic story of creation and destruction. They revealed heavy elements like oxygen, silicon, and iron, forged in the nuclear furnaces of massive stars and then scattered into space by supernova explosions. Finding these elements in the wind was a smoking gun. It directly implicated starburst activity as a primary source. The wind was quite literally carrying the ashes of dead stars out of the galaxy. But the plot quickly thickened. In many winds, especially the most powerful ones, the chemical signatures were far more complex. They showed an overabundance of certain elements and even the presence of highly ionized gas, atoms stripped of many electrons, which requires an immense flood of energetic radiation. This pointed a finger squarely at the active galactic nucleus, the supermassive black hole. Its intense glare was not just pushing gas, it was superheating it and stamping it with a unique high-energy signature. So the investigation took a surprising turn. It was not a simple case of one or the other. The chemical evidence suggested that both suspects were often at the scene of the crime, sometimes working together. A burst of star formation could create a wind, which then funnels material toward the central black hole, feeding it and awakening the monster. The black hole then unleashes its own, even more powerful outflow, which can shock and compress the surrounding gas, potentially triggering a new round of star formation even as it shuts down activity elsewhere. This intricate chemical dance revealed that galactic winds are not just destructive forces. They are the universe's primary recycling system. They gather up the enriched elements from one generation of stars and blast them out into the vast intergalactic medium, seeding future generations of stars, planets, and perhaps even life with the essential building blocks for everything from rocky worlds to living organisms. The iron in your blood and the calcium in your bones were once part of a star that lived and died billions of years ago, and a galactic wind helped deliver those ingredients across the cosmos. This brings us face to face with the ultimate cosmic engine, the supermassive black hole. Tucked away in the heart of nearly every large galaxy, these gravitational monsters are not merely passive voids. When they feed, they transform into the most powerful energy sources in the universe, capable of dictating the fate of everything around them. Their influence on galactic winds is both spectacular and terrifying. Picture a whirlpool of gas and dust, an accretion disk spiraling into the black hole's event horizon. This material does not go quietly. Friction heats it to millions of degrees, causing it to blaze with radiation across the entire electromagnetic spectrum. This is what astronomers call an active galactic nucleus, and in its most luminous form, a quasar. The sheer pressure from this intense radiation can be so overwhelming that it physically pushes the surrounding gas and dust, accelerating it outward in a vast, spherical wind that can sweep across the entire galaxy. But radiation pressure is only part of the story. Some of the infalling material gets channeled and focused by the black hole's immensely powerful magnetic fields. Instead of falling in, this material is shot out from the poles at nearly the speed of light, forming colossal jets that can pierce through intergalactic space for hundreds of thousands of light years. These jets are not gentle streams, they are focused beams of pure energy, slamming into the galaxy's reservoir of cold gas, the very fuel for new stars. The impact is catastrophic, heating the gas to such extreme temperatures that it can no longer collapse to form stars. In this way, a single supermassive black hole can effectively sterilize its own galaxy, shutting down star formation not with a whisper but with a roar. The entire galactic ecosystem is held in a delicate balance, teetering between creation and destruction, all dictated by the feeding habits of a dark heart at its center. How could anything, even a galaxy, survive such an onslaught? Survival often depends on a delicate balance between creation and destruction. While the black hole's fury is immense, another powerful force is constantly at work, one born from the brilliant light of newborn stars themselves. This is the fourth clue, the feedback from star formation. In regions of frantic stellar birth known as starbursts, the galaxy is buzzing with youthful energy. But this very act of creation sows the seeds for its own limitation. The most massive stars born in these nurseries are spectacularly short-lived. They burn through their nuclear fuel in only a few million years, a cosmic blink of an eye. Their final act is a supernova explosion, a detonation so violent it can outshine an entire galaxy. Now, imagine not just one, but thousands of these explosions rippling across a galactic disk. The combined effect is like a continuous cosmic bombardment. Each blast injects a tremendous shockwave of energy and momentum directly into the surrounding clouds of gas and dust, the raw material for future stars. This collective force acts like a piston, violently pushing the surrounding interstellar medium outward, driving a powerful wind from the galaxy's core. But the supernova are not the only players. Even before they explode, these massive stars are shaping their environment. They flood space with intense ultraviolet radiation and powerful stellar winds, streams of charged particles flowing from their surfaces. This constant radiation pressure pushes against the gas, much like the heat from the sun pushes against a comet's tail, helping to clear out cavities and further energize the medium. This entire cycle is a beautiful, self-regulating feedback loop. A dense cloud collapses to form a generation of stars. The most massive of those stars then proceed to blast and irradiate their surroundings, driving a wind that disperses the very gas that could have formed the next generation. It is a celestial case of a boom and bust economy, where a period of rapid growth is inevitably followed by a slowdown. This stellar feedback ensures that galaxies do not consume all their fuel in one frantic burst of star formation. It paces the galaxy's evolution, stretching its star-forming history over billions of years and preventing it from burning out too quickly. So the question becomes, how do these two titanic forces, the black hole and the starburst, interact to sculpt a galaxy's long-term destiny? The forces of black holes and starbursts leave behind a chaotic crime scene, but to understand the full scope of their impact, we needed to see the shape of the hurricane itself. The fifth clue arrived as we finally mapped the anatomy of these galactic winds. For decades, they were little more than spectral smudges, but advanced telescopes have peeled back the blur, revealing structures of breathtaking complexity and scale. The Hubble Space Telescope, with its unparalleled sharpness in visible and ultraviolet light, showed us that these are not simple, billowing clouds. It captured vast filamentary networks, delicate tendrils of gas stretching for tens of thousands of light years, looking more like intricate cosmic spiderwebs than a formless fog. These filaments are the scars of immense violence, where shock waves from supernova or black hole jets have ripped through the galactic medium, leaving behind a tangled web of condensed and ejected material. Then came the Atacama Large Millimeter Array, or ALMA, a network of radio telescopes high in the Chilean desert. ALMA peers at a different part of the light spectrum, one that sees the cold, dense molecular gas, the very fuel for stars. Astonishingly, ALMA found that these powerful winds are not just made of hot, ionized gas. They are also carrying away colossal amounts of this cold star-forming material, sometimes enough to build billions of suns. This was a revelation. The wind was not just heating the gas and shutting down star formation, it was physically stealing the galaxy's future fuel right out of its hands. Now the James Webb Space Telescope, with its infrared eyes, is looking even deeper. It can see through the obscuring dust that often hides the inner workings of a galactic core, revealing the precise launch point of these outflows. It shows how the wind originates and how it evolves as it travels, allowing us to witness the direct interaction between the black hole's fury and the surrounding gas in real time. By combining these multi-wavelength views, we get a complete three-dimensional picture. We can see the hot gas glowing in X-rays, the warm ionized gas in visible light, and the cold molecular streams in radio waves, all moving together in a coordinated yet chaotic exodus. This detailed mapping proves that galactic winds are not a single entity, but a multi-phase structured system, a complex ecosystem in its own right. But seeing these structures in the modern universe was only the beginning. The true test of their importance lies in their legacy, a fossil record written across cosmic time. The sheer speed of these outflows is what makes them so formidable. To understand their power, we must measure their velocity, and for that, astronomers turn to a fundamental principle of physics, the Doppler shift. Just as the pitch of a siren drops as an ambulance races away from you, the light from a receding gas cloud is stretched, shifting its color toward the red end of the spectrum. By measuring this redshift with exquisite precision, we can clock the wind's speed. The numbers are staggering. We see gases hurtling outward at several million miles per hour, far exceeding the escape velocity of even the most massive galaxies. This simple measurement, the kinematic signature, is a direct window into the engine driving the wind. A wind powered primarily by supernovae will have a certain velocity profile, a specific spread of speeds that reflects the combined chaotic pushes of thousands of explosions. In contrast, a wind driven by the focused radiation or jets from an active galactic nucleus often shows much higher velocities and a different kinematic structure, a cleaner, more focused blast. The data reveals a complex reality. Often, we see multiple velocity components superimposed, a slower, broader flow from stellar feedback with a faster, more energetic stream embedded within it, the unmistakable fingerprint of the central black hole adding its immense power to the exodus. This velocity dispersion is the key to unlocking the wind's energy budget. By calculating the mass and speed of the outflowing material, astronomers can work backward to determine the minimum amount of energy required to launch it. The answers consistently point to events of almost unimaginable violence, requiring the combined output of millions of supernovae or the focused fury of a feeding supermassive black hole. These kinematic signatures solve a critical puzzle, explaining how the wind not only starts its journey but successfully completes it. A galaxy's gravity is immense, a powerful grip that should hold onto its gas. For the wind to escape, it must be given a truly phenomenal kick, a burst of acceleration that overcomes this gravitational pull in a single, decisive shove. The velocity profiles we observe are the record of that kick, the definitive proof of a power struggle where the forces of creation and destruction have momentarily triumphed over the galaxy's own weight. This raises a profound question. If these winds are so effective at stripping galaxies, how does any star-forming gas remain at all? The true legacy of these cosmic hurricanes is written in the emptiness they leave behind. Galactic winds act as the ultimate regulators of galactic ecosystems, governing the life and death of stars with a heavy hand. Their most immediate impact is a brutal form of galactic cleansing. By expelling colossal amounts of gas, they directly rob a galaxy of its star-forming fuel. This is not a gentle process. It is an eviction, a forcible removal of the very atoms that would have collapsed to birth new suns. A galaxy can be left gas-poor, its stellar nurseries shutting down one by one as the raw material is swept away. This suppression of star formation is the primary reason why some massive galaxies are essentially dead, filled with aging red stars and devoid of the blue light of youthful stellar populations. They have had their future stolen by the wind, yet nothing in the cosmos is truly wasted. The material ejected from the galaxy does not simply vanish into the void. It is blown far out into the vast, mysterious region known as the circumgalactic medium, the halo of thin gas that surrounds every galaxy. Here, the wind performs a vital function, enriching this pristine environment with the heavy elements forged in stellar furnaces. This process transforms the circumgalactic medium from a barren reservoir of primordial hydrogen and helium into a rich soup of oxygen, carbon, and iron. This enrichment has profound consequences for the galaxy's future. When new gas eventually falls back in, perhaps drawn in by a merger with a smaller galaxy, it will already be seeded with the elements necessary to form rocky planets and potentially the chemistry for life. The wind, in a beautiful paradox, is both a destructive force and a vital delivery service. Over billions of years, this continuous cycle of expulsion and enrichment sculpts the galaxy's very shape. A powerful wind can blow away loose gas from the galactic disk, preventing it from settling and forming new stars, which helps maintain the clean, elegant structure of a spiral galaxy. In more extreme cases, relentless feedback can halt the growth of a galaxy entirely, stunting it and leaving it as a compact, red and dead elliptical. The galactic ecosystem is therefore a delicate balance between the inward pull of gravity, gathering gas to build stars, and the outward push of the wind, regulating that growth and seeding the cosmos with the ingredients for future generations. The question is no longer whether these winds are powerful, but how far their influence truly reaches. Yet the reach of these winds is not infinite. Their journey into the void is governed by an unseen force, a ghostly presence that holds the entire galaxy in its gravitational grip. This brings us to the eighth clue, the hidden connection between galactic winds and dark matter. Every galaxy, including our own Milky Way, is embedded within a vast, invisible sphere of dark matter, a halo that extends far beyond the visible stars. This dark matter does not emit any light, but its gravitational pull is the primary anchor, the cosmic glue that keeps the galaxy from flying apart. This invisible halo acts as a deep gravitational well, and the wind must climb out of it to truly escape. The shape and depth of this well are critical. A massive, concentrated dark matter halo creates a steep, powerful gravitational slope. A wind needs enormous energy to overcome this and carry material all the way into intergalactic space. If the wind lacks that ultimate punch, the ejected gas will reach a certain height, slow, and then fall back into the galaxy in a cosmic rain, eventually fueling new rounds of star formation. This is galactic recycling on the grandest scale, but if the dark matter halo is less massive or more spread out, the gravitational well is shallower. In that case, even a moderately powerful wind can successfully push material over the edge, permanently depriving the galaxy of those resources and effectively quenching its growth. This relationship solves a long-standing puzzle. Why do some galaxies seem to recycle their winds while others expel them forever? The answer lies in the properties of their invisible dark matter halos. These ghostly structures are the ultimate arbiters, the invisible walls that can either confine a wind's fury or allow it to bleed away into the cosmos. They shape not just the fate of the gas, but the ultimate size and destiny of the galaxy itself. What other invisible forces are silently guiding the evolution of the universe? But the wind is never just one thing. It is a chaotic mixture of states, a cosmic storm where different forms of matter collide and coexist. This ninth clue is the multiphase nature of the wind itself. We are not looking at a simple, homogeneous stream of gas. Instead, these outflows are a complex tapestry woven from three distinct threads, hot, warm, and cold, all flowing outward together in a violent and precarious dance. The hot phase is a tenuous plasma, a gas so incredibly heated by supernova shocks or black hole radiation that its atoms are ripped apart, leaving behind a soup of ions and electrons that glows fiercely in X-rays. This component provides the powerful, energetic pressure that helps drive the entire outflow. Intermingled with it is the warm phase, ionized gas that we see glowing in visible and ultraviolet light, the brilliant filamentary structures captured by Hubble. Then, most surprisingly, there is the cold phase. This is the dense molecular gas, the same raw material that forms stars, somehow surviving its tumultuous journey through the inferno. Its presence is a profound puzzle. How can delicate clouds of cold gas endure being blasted through a scorching plasma wind? Their survival suggests a frantic process of cooling and shielding. As the hot wind plows through the galaxy, it can crush and shatter colder clouds, but it can also trigger their formation. The immense pressure from the surrounding heat might actually squeeze smaller pockets of gas, causing them to collapse and cool even further, like ice crystals forming in the exhaust of a rocket. This constant interplay between heating and cooling, destruction and creation, makes the wind incredibly difficult to model. Simple simulations fail to capture the delicate balance that allows these phases to persist side by side. The multiphase structure is a critical clue to the wind's true efficiency. The cold molecular gas is heavy, carrying a huge amount of mass and momentum. If it can survive the journey, it means the wind is stripping the galaxy of its most valuable star-forming fuel directly. Meanwhile, the hot gas acts as a high-pressure piston, pushing the entire structure forward. This complexity reveals that galactic winds are not just simple exhaust systems. They are dynamic, self-regulating ecosystems where the fate of the galaxy is decided by a constant, turbulent battle between temperature and density. A battle whose outcome determines whether a galaxy will continue to create new stars or fall silent. The specific personality of a galactic wind is shaped by the galaxy it calls home. Not all galaxies produce the same kind of outflow, and by comparing them, we uncover a spectrum of cosmic behavior. In the intense firestorm environments of starburst galaxies, the winds are incredibly prolific. These are galaxies undergoing a feverish burst of star formation, often triggered by a collision or merger. Here, the wind is dominated by the collective fury of supernovae, a chaotic and widespread exodus. The mass loss rates are staggering, with these galaxies ejecting the equivalent of hundreds or even thousands of suns worth of material every single year. It is a spectacularly wasteful process where the galaxy is expelling its future at a breathtaking pace, a desperate attempt to quell its own explosive birth rate. In stark contrast, the winds from massive elliptical galaxies tell a story of a quieter, more settled existence. These are often red and dead galaxies where star formation has long since ceased. The winds we detect here are different. They are frequently hotter, more diffuse, and are often powered by the residual heat from aging stellar populations or the occasional, low-level activity of the central black hole. Instead of a violent blast, it is more like a steady, hot breath, a galactic exhalation that helps maintain the galaxy's quiescent state by preventing any lingering cool gas from collapsing. The energetics are lower, the mass loss is slower, but the effect is just as final. Then there are the dwarf galaxies, the small, fragile building blocks of the cosmos. For them, a galactic wind is not just a regulatory mechanism, it can be a death sentence. Dwarf galaxies have shallow gravitational wells, meaning their grip on their own gas is tenuous at best. Even a modest outflow, driven by a small burst of star formation, can achieve escape velocity with ease. The wind does not just suppress future star formation, it can strip the galaxy bare, permanently halting its growth and leaving it a dark, gas-poor relic. This explains why we see so many faint, inert dwarf galaxies in the universe. They are the cosmic casualties, the small creatures blown clean by winds they could not withstand. This variation across galaxy types paints a complete picture of galactic evolution, from the frantic, youthful outflows of starbursts to the weary sighs of aging giants and the catastrophic blowouts that stunt the smallest systems. Each wind is a chapter in its galaxy's biography, written in the language of escaping gas. But to read the very first chapters, we must look back to the dawn of time itself. Deep within the turbulence of these cosmic storms lies an invisible architect, a force that guides the chaos into coherent form. This is the 11th clue, the subtle but powerful role of magnetic fields. We often think of these outflows as simple gas pushed by thermal pressure or radiation, but that picture is incomplete. Without a guiding hand, such a violent expulsion would simply be a disordered, billowing cloud, quickly losing its momentum and structure. Magnetic fields provide that structure. They are the cosmic threads woven through the interstellar medium, and when a wind is launched, these fields are dragged along and amplified, acting like a funnel. They collimate the outflow, channeling the chaotic energy into a more focused, directed stream, much like putting your thumb over the end of a garden hose creates a tight jet of water. This collimation is crucial for the wind's longevity, allowing it to travel vast distances without dissipating into a harmless mist. But how do we observe something as intangible as a magnetic field? The evidence comes from a phenomenon called polarization. As dust grains in the wind align themselves with the magnetic field lines, they emit light that is polarized, vibrating in a preferred direction. By carefully measuring this polarized light with radio telescopes, astronomers have mapped the magnetic fields in several galactic outflows. The results are stunning, revealing vast, ordered magnetic structures stretching for thousands of light years, directly tracing the architecture of the wind itself. These are not random fields, they are organized, coherent guides shaping the exodus. The theoretical framework that explains this is magnetohydrodynamics, a complex dance where magnetic fields and electrically conducting fluids like plasma influence each other. Models show that these magnetic forces can stabilize the wind, preventing it from fragmenting as it rams into the surrounding galactic halo. They can also transfer momentum efficiently, helping to accelerate cold clouds that would otherwise be left behind. The magnetic field is the silent conductor of this cosmic orchestra, ensuring the different phases of the wind, the hot, warm, and cold, move in a coordinated, though still violent, symphony. It is a fundamental piece of the puzzle, explaining how these immense structures maintain their integrity across millions of years, directly shaping how effectively a galaxy can regulate its own growth. Beyond the heat and light, another invisible force surges through these cosmic storms. Galactic winds are not just rivers of gas, they are powerful particle accelerators, generating a relentless flood of cosmic rays. These are not rays of light, but atomic nuclei, mostly protons, stripped of their electrons and hurled through space at nearly the speed of light. They are the most energetic particles in the universe, and their origin has long been a mystery. We now know that the violent shocks within galactic winds are one of their primary breeding grounds. When a supernova blast wave or a black hole jet slams into the surrounding gas, it creates a chaotic frontier, a moving wall of immense pressure. Protons and other atomic nuclei get caught in this magnetic turbulence, bouncing back and forth across the shock front, gaining a little more energy with each pass until they are ejected as ultra-relativistic cosmic rays. This process turns the entire wind into a colossal natural accelerator, one that operates on a scale far beyond anything we could ever build on Earth. But these cosmic rays are more than just energetic souvenirs. They are active participants in the wind's journey. Once created, they fill the outflow with a diffuse, hot gas of their own. Unlike normal gas, this cosmic ray gas exerts a special kind of pressure, a persistent and penetrating force that pushes outward on the surrounding material. It acts like a steady, invisible hand, helping to inflate the wind and propel it forward, supplementing the push from thermal pressure and radiation. This solves a key problem in wind dynamics. In some galaxies, the thermal pressure from hot gas alone does not seem sufficient to explain the observed speeds and mass loss rates. The additional pressure from cosmic rays provides that missing push, a continuous boost that helps the wind overcome the galaxy's gravity and carry its heavy load of cold gas into the halo. The wind, therefore, is a three-phase system powered by a trio of forces: thermal pressure from hot gas, radiation pressure from starlight and black holes, and the non-stop push from this sea of high-energy particles. It is a complex engine where every component, even the most ghostly, plays a vital role in shaping the galactic ecosystem. These cosmic storms are not eternal. Like hurricanes on Earth, they have a life cycle, a dramatic arc of birth, maturity, and eventual decay. The 13th clue forces us to consider time, tracing the entire evolution of a galactic wind from its explosive ignition to its final, fading whisper. The triggering event is sudden and violent, a period of intense starburst activity or the awakening of the central black hole. This ignition phase is a firestorm, a brief but incredibly energetic outburst that launches the wind at its maximum power and velocity. For a few million years, the outflow rages, a blistering front of energy and matter that carves its way through the galaxy's interstellar medium. This is the wind in its youth, raw and untamed. Then comes a long, slow maturity. As the starburst fades or the black hole's fuel supply dwindles, the engine's power begins to wane. The wind no longer receives the same intense, continuous push. It begins to coast, expanding into the circumgalactic medium, but its speed gradually decreases. During this phase, the wind's structure becomes more complex as different phases of gas begin to separate and interact with the surrounding halo. Finally, after hundreds of millions of years, the wind enters its dissipation phase. Its velocity drops below the escape velocity of the galactic halo and the outflow stalls. The hot gas may slowly blend back into the halo's atmosphere, while denser, colder clumps of material begin to fall back toward the galaxy in a process known as galactic fountain flow. The mighty hurricane dissipates into a gentle, raining mist, but does any evidence of this ancient violence remain? Absolutely. This is where the concept of fossil winds becomes crucial. We can still detect the ghosts of these long-dead outflows. In many seemingly quiet galaxies, we observe vast, faint shells or bubbles of hot, ionized gas lingering far out in the galactic halo. These are the fossilized remnants of a wind that blew billions of years ago. They are the cosmic equivalent of a blast crater, a permanent scar recording a past cataclysm. By studying the size, temperature, and chemical composition of these fossil winds, astronomers can perform galactic archaeology. They can read this fossil record to determine when the wind was launched, how powerful it was, and what kind of event, a starburst or a quasar, was responsible. These silent, enduring structures are time capsules, offering us a direct window into the most tumultuous chapters of a galaxy's history, long after the fires that drove them have gone cold. What other ancient echoes are waiting to be heard in the darkness between the stars? The journey of a galactic wind does not end at the edge of its home galaxy. Its true cosmic purpose is fulfilled when it slams into the vast, near-empty expanse of the intergalactic medium, the thin plasma that fills the space between galaxies. This collision is not a silent impact. It is a transformative event that reshapes the environment on the largest scales imaginable. When a powerful wind meets this tenuous outer gas, it acts like a plow, sweeping up material and pushing it ahead, creating a colossal bubble of shocked, heated gas that can span hundreds of thousands of light years. These are not mere clouds, they are galactic-scale structures, immense cavities blown into the intergalactic medium that mark a galaxy's sphere of influence. Inside these bubbles, the conditions are chaotic. The wind's material mixes with the primordial gas, enriching it with a fresh supply of heavy elements. This is the ultimate destination for the iron and oxygen forged in stellar furnaces, a dispersal mechanism that pollutes the entire cosmic neighborhood with the seeds for rocky worlds and, potentially, life. Yet, gravity never fully relinquishes its claim. Not all the ejected gas achieves permanent escape. Much of it, especially the denser, colder clouds, reaches a certain height in the galactic halo, only to stall, cool, and fall back toward the disk in a magnificent cascade known as a galactic fountain. Picture a colossal waterfall in space where rivers of gas, having been flung thousands of light years upward, now rain back down in brilliant filaments, splashing onto the galactic disk and reigniting star formation in a new location. This continuous cycle of expulsion and return is a critical part of the Grand Baryon cycle, the universal process that governs the flow of normal matter. Galactic winds are the vital link that moves baryons, the particles that make up stars and planets, out of galaxies and into the circumgalactic and intergalactic realms. They are the primary mechanism for solving the cosmic missing baryons problem, explaining where a significant portion of the universe's normal matter has been hiding, not in galaxies themselves, but in these vast, enriched halos and bubbles. The wind, therefore, is far more than a local event. It is a fundamental conveyor belt in the cosmos, a force that connects the fate of a single galaxy to the chemical evolution of the entire universe, ensuring that no star lives and dies in vain. What other invisible currents flow through the cosmic ocean, connecting island universes across the void? The invisible physics of these cosmic hurricanes are far too complex for simple equations alone. To truly grasp their behavior, we must build digital universes inside supercomputers, a realm where the 15th clue comes to life through numerical simulations and theoretical models. These are not simple animations, they are vast mathematical experiments that recreate the laws of physics on a galactic scale. Every parcel of gas, every burst of energy, and every shockwave is calculated using hydrodynamical codes which simulate the flow and interaction of fluids. But the sheer range of scales is staggering, from the tiny region around a single supernova to the million light-year sweep of the wind itself. It is impossible for any computer to track every single star and every wisp of gas. This is where subgrid physics comes in, a set of brilliant mathematical shortcuts that allow scientists to approximate the small-scale chaos, like the average effect of thousands of supernovae, without having to simulate each one individually. Without these models, the violent emergence of a galactic wind would remain a beautiful mystery. With them, we can run experiments. We can watch what happens when we turn up the power of a starburst or dial down the activity of a black hole. We can see how magnetic fields twist and channel the outflow, and we can track how cosmic rays percolate through the system, providing that extra push. The simulations reveal non-linear processes where small changes can have enormous, unpredictable consequences. A slight increase in density might lead to a runaway cooling effect, forming massive cold clouds within the hot flow, exactly as our telescopes have observed. These digital laboratories allow us to test our theories against reality. Researchers can run a simulation that produces a virtual galactic wind, then generate a synthetic observation, a prediction of what our telescope should see. Does the model produce the same mix of hot and cold gas, the same velocity profiles, the same chemical fingerprints? When the simulation matches the data, we know we are on the right track. When it fails, it forces us back to the drawing board to question our assumptions and discover new physics. These virtual winds are our proving grounds, the crucial bridge between raw theory and the hard, beautiful truth of the cosmos. The faint light from the universe's first galaxies carries a hidden message about cosmic chaos. When we point our most powerful telescopes at the most distant, ancient objects we can find, we see the unmistakable signatures of galactic winds, already blowing fiercely when the cosmos was less than 1 billion years old. These were not the refined outflows of modern galaxies. These were primordial hurricanes unleashed in a universe that was denser, hotter, and filled with the first incredibly massive stars. The feedback from these stellar giants must have been apocalyptic. Their supernovae were far more violent than anything we see today, and their intense ultraviolet radiation blasted the surrounding gas, driving powerful winds that fundamentally shaped the infant cosmos. These primordial outflows were crucial for a pivotal cosmic transition known as reionization. After the Big Bang, the universe cooled into a fog of neutral hydrogen gas. The first stars and galaxies began to blaze, and their intense radiation, amplified and spread by these early winds, acted like a cosmic sunrise, burning away the fog and ionizing the hydrogen, rendering the universe transparent to light for the first time. Without these winds to carve out bubbles and channels, the reionization process might have been slow and patchy. Instead, they helped flood the cosmos with the energetic photons that cleared the way for the universe we see today. But their role was not merely one of illumination. These winds were also the first great regulators. In the early, clumpy universe, gravity was eager to pull gas together into monstrously large galaxies. The winds provided a necessary counterbalance, blowing out the gas from these first structures and preventing them from growing too large too fast. They effectively put a speed limit on galactic growth, ensuring the first galaxies remained small and manageable, setting the stage for the diversity of galaxy types we observe later. Most profoundly, these ancient winds were the universe's first recycling program. The first stars, known as population 3 stars, were pure hydrogen and helium, but they lived fast and died in colossal explosions, forging the first heavy elements in their cores. The galactic winds that followed their death swept these newly minted atoms, the first oxygen, carbon, and iron, out of their host galaxies and into the pristine intergalactic medium. This first pollution event was essential for all that followed. It seeded the cosmos with the raw materials for rocky planets, for water, and for the chemistry of life itself. Every element in our bodies beyond hydrogen and helium can trace its lineage back to those first stars and the powerful winds that scattered their ashes across the infant universe, a legacy of violence that made our existence possible. For decades, astronomers faced a cosmic accounting error of epic proportions. When they tallied up all the normal matter, the baryons that make up stars, planets, and us, there was a staggering shortfall. Roughly half of the universe's expected ordinary matter was simply missing. The answer to this enigma, it turns out, was blowing in the wind. Galactic winds are the primary delivery system for this missing material. They act as cosmic conveyor belts, taking the heavy elements and normal matter from within galaxies and launching them on a one-way trip into the vast, hard-to-detect regions of intergalactic space. But why is this matter so difficult to find once it leaves the galaxy? The ejected gas is spread incredibly thin and heated to millions of degrees by the violence of its expulsion. At these temperatures, it does not glow in visible light. It emits a faint, diffuse fog of X-rays that is incredibly challenging for our telescopes to detect against the background of the universe. It is like trying to spot the heat of a single candle from miles away. By studying the mechanics of galactic outflows, we can finally trace this journey. We can calculate how much mass is being ejected at what speeds and predict where this enriched material should end up, hidden in the warm, hot intergalactic medium that filaments the cosmos. This solves the missing baryon problem not by finding new matter, but by understanding the universal process that hid it in plain sight. The very winds that shape galaxies are also responsible for filling the spaces between them with a faint, hot breath of former stars, completing the inventory of the cosmos. The scale of these winds expands beyond single galaxies into the most massive structures in the universe. Inside colossal galaxy clusters, the collective breath of thousands of galaxies merges into a single cluster-wide gale. Each individual wind contributes, but the dominant force often comes from the supermassive black hole at the cluster's very heart, residing in the central giant elliptical galaxy. This monster's outbursts are so immense they can blow bubbles of pure radio emission, cavities that rise through the hot intracluster medium like cosmic hot air balloons. These bubbles push aside the multimillion-degree gas that binds the cluster together, redistributing its energy and preventing a catastrophic cooling flow. Without this feedback, the dense core of the cluster should cool rapidly, funneling vast rivers of cold gas toward the center at a rate of thousands of suns per year. This gas will be expected to form a spectacular burst of new stars, creating one of the brightest objects in the universe. Yet we do not see this. The predicted starbursts are missing, and the central galaxies remain relatively quiet. The galactic winds on this immense scale provide the explanation. The energy injected by the combined outflows, particularly from the central black hole, acts as a cosmic thermostat. It stirs the intracluster medium, heating it just enough to balance the relentless pull of radiative cooling. This feedback loop stabilizes the entire cluster for billions of years, preventing it from either freezing over in a deluge of cold gas or blowing itself completely apart. It is a delicate equilibrium played out across millions of light years, where the combined size of countless galaxies and the roar of a single black hole work in concert to govern the life and death of stars on an almost unimaginable scale. How does this intricate balance leave its mark on the galaxies caught within the storm? Detecting these cosmic storms requires a toolbox of astronomical techniques, each tuned to a different layer of the wind's complex anatomy. The evidence arrives not in a single flash of light, but across the entire electromagnetic spectrum, a symphony of signals that we must learn to interpret. In the high-energy realm of X-rays, space telescopes like Chandra capture the faint, diffuse glow of the wind's hottest phase, the superheated plasma at millions of degrees. This reveals the raw, energetic engine driving the entire outflow. Meanwhile, the Hubble Space Telescope, observing invisible and ultraviolet light, maps the brilliant filaments of the warm, ionized gas, tracing the wind's intricate web-like structure as it stretches into the galactic halo. To find the cold, star-forming fuel caught in the gale, astronomers turn to radio telescopes like ALMA. These instruments detect the faint whispers of molecules like carbon monoxide, revealing the surprising presence of dense, cold clouds racing alongside the scorching plasma. Each wavelength is a different instrument in the orchestra, and only by listening to all of them can we hear the full, tumultuous music of the wind. But listening is not the same as understanding. Each observational technique comes with its own set of formidable challenges. The first is resolution. Even with our most powerful telescopes, a distant galaxy is often just a tiny smudge of light. We are trying to map the intricate details of a hurricane from thousands of miles away. This makes it incredibly difficult to distinguish the fine structure of the wind, to see if it is a smooth flow or a collection of discrete crashing clouds. Then there is the problem of projection effects. When we look at a galaxy, we see it flattened into two dimensions on the sky. A stream of gas that appears to be blowing directly outwards might in fact be moving at a steep angle or even orbiting within the galaxy's halo. We are trying to reconstruct a three-dimensional explosion from a single, flat photograph, a cosmic illusion that can easily mislead us. Perhaps the most subtle challenge is distinguishing a true galactic wind from other phenomena. The universe is full of moving gas. Is that cloud part of a wind, or is it a tidal stream ripped from a smaller galaxy during a merger? Is that redshift due to the Doppler shift of an outflow, or is it the simple expansion of the universe stretching the light? Untangling these possibilities requires painstaking analysis, combining data from multiple wavelengths to build a consistent, three-dimensional picture of the motion. It is a meticulous forensic science where every clue must be cross-examined before we can confidently point to the wind as the culprit. After piecing together this complex evidence from our own cosmic neighborhood, we are left with a profound question. Does our own Milky Way galaxy, our home, possess such a powerful wind? This constant scattering of stellar material makes galactic winds the universe's most prolific polluters. They take the heavy elements created in stellar cores and supernova blasts and fling them far beyond their birthplace, fundamentally altering the chemical composition of the cosmos. Think of it as a cosmic form of agriculture. Stars are the plants that grow from the primordial soil of hydrogen and helium. When they die, they produce rich fertilizer, elements like oxygen, carbon, and nitrogen. Galactic winds are the great storms that sweep across the fields, distributing this fertilizer far and wide, ensuring that the next generation of stars and planets grows from soil that is already enriched and ready for complexity. Without this process, the universe would be a much simpler and far less interesting place. entire galaxies would remain composed only of the two original elements, unable to form the rocky planets or the complex chemistry that is the foundation of life. This pollution is measured by astronomers as metallicity, the percentage of a galaxy's mass that is made up of elements heavier than hydrogen and helium. A galaxy with a high metallicity is one that has been thoroughly processed by multiple generations of stars and thoroughly polluted by its own winds. The winds ensure this enrichment is not a local event. They carry these metals out of the galactic disk and inject them deep into the circumgalactic medium, the vast halo of gas that surrounds a galaxy. When new gas, pristine and metal-poor, later falls into the galaxy from intergalactic space, it mixes with this enriched reservoir. The next cycle of star formation therefore begins from a richer chemical base. This is why older stars in our own galaxy tend to have lower metallicity, while younger stars like our Sun are metal-rich. They were born from gas that had been repeatedly seeded by the winds of long-dead stellar generations. The very iron in our blood and the calcium in our bones were once part of a star that lived and died billions of years ago, and a galactic wind was the delivery system that brought those crucial ingredients into the mix that would one day form our solar system. This pollution is not a flaw in the cosmic system. It is the essential process that builds the ingredients for worlds like our own. How far has this cosmic contamination spread, and what does it mean for the possibility of life elsewhere in the universe? The ultimate destination of this escaping gas defines the galaxy's future. Some of the ejected material, particularly the densest, coldest clouds, never truly breaks free. After being flung thousands of light years upward, it reaches the apex of its trajectory, slows, and then begins a long, graceful fall back toward the galactic disk. This is the galactic fountain, a magnificent cycle of expulsion and return where rivers of enriched gas rain down upon the spiral arms, splashing into the interstellar medium and potentially seeding new sites of star formation. This returning rain is a form of cosmic recycling, allowing the galaxy to reuse its own processed materials. Yet not every particle comes home. A significant portion of the wind, especially the hotter, more diffuse gas, achieves a velocity high enough to overcome the galaxy's gravitational pull completely. This material escapes the disk and the inner halo, but it does not vanish into nothingness. Instead, it joins the circumgalactic medium, the vast and mysterious reservoir of gas that surrounds the galaxy like an immense invisible atmosphere. Here it lingers for billions of years, a hot, enriched fog that is loosely bound to the galaxy's dark matter halo. This circumgalactic reservoir acts as a long-term storage tank, a place where the galaxy's heavy elements are kept in reserve. In the future, gravitational perturbations from galactic mergers or the gentle cooling of this halo gas might cause some of this material to eventually fall back, fueling a new era of star formation far in the future. But for the most energetic outflows, the journey is final. The fastest, hottest material, driven by the most violent quasar eruptions, can achieve escape velocity from the entire dark matter halo itself. This gas is permanently lost, cast adrift into the true intergalactic void to become part of the warm, hot intergalactic medium, the cosmic web of filaments that connects all clusters and galaxies. This final, irreversible loss is what truly quenches a galaxy. Each atom that escapes forever is a piece of the galaxy's future that is stolen, a permanent reduction in its potential to build new stars and planets. The long-term sustainability of a galaxy therefore hinges on this delicate balance between the fountain and the hemorrhage. A galaxy that efficiently recycles its winds through fountains can sustain a slow, steady rate of star formation for billions of years. A galaxy whose winds are too powerful, blowing its gas clear out of the halo, is a galaxy destined to grow old and fade, its stellar population aging without renewal. The fate of every galaxy is written in the trajectory of its escaping breath. a choice between a cyclical renewal and a slow, cosmic exhalation into the infinite dark. The sheer violence of these outflows leaves a permanent mark on a galaxy's very architecture. Galactic winds directly influence a fundamental structural property known as the scale height. Think of a spiral galaxy like our own Milky Way, not as a flat pancake, but as a slightly puffed-up disk with layers of gas and stars extending above and below the central plane. The average distance that this material rises from the midplane is its scale height. A calm, settled galactic disk has a relatively small scale height, its gas and stars held in a tight, orderly plane by gravity. But introduce a powerful wind, and this calm geometry is shattered. The wind acts like a powerful updraft, inflating the disk from within. As the outflow blasts its way out of the galaxy, it does not take a perfectly clean, vertical path. It shoves and pressurizes the interstellar medium around it, creating bubbles and cavities that lift the entire gaseous disk, making it thicker and more turbulent. This process effectively pumps energy into the vertical motions of the gas, causing it to billow outward and form a much more substantial, fluffier structure. We can observe this directly in galaxies with strong winds, where the gaseous disk appears noticeably thicker and more disturbed compared to quiescent galaxies of similar mass. This inflation has profound consequences. A thicker disk is a less efficient one for star formation. In a thin disk, gas clouds can easily collide and collapse under their own gravity. But in a puffed-up, high-pressure environment, those same clouds are kept apart and stabilized, stifling the birth of new stars. The wind, therefore, leaves a dual legacy. It ejects material entirely while also heating and thickening the gas that remains behind, applying a long-term brake on galactic activity. This altered structure is a fossil record of past outflows. By measuring the scale height of the gas in a distant galaxy, astronomers can infer the historical strength of its winds, reading the violence of its past in the present-day puffiness of its disk. The galaxy's own shape becomes a silent witness to the storms that have shaped it. Deep within the wind's chaotic flow, a hidden battle of forces dictates its final form. This 23rd clue confronts the turbulent heart of the storm, where the smooth physics of a textbook fluid gives way to a wild, unpredictable froth. Turbulence is the hallmark of this chaos, the same churning motion you see in a rushing river or a billowing thundercloud, but scaled up to galactic proportions. It arises from shear, where different streams of gas move at vastly different speeds, ripping each other apart into a whirlwind of eddies and vortices. This turbulence is not just a side effect, it is a primary architect. It shreds the wind from the inside, preventing it from being a simple, conical flow, and instead molding it into the intricate, filamentary webs our telescopes observe. These whirlpools act as cosmic blenders, vigorously mixing the different phases of the wind, the hot, warm, and cold, ensuring they exchange energy and momentum in a frantic dance. Without this mixing, the cold clouds might simply coast along, isolated, but turbulence ensures they are constantly ablated and eroded, gradually dissolving their mass back into the hotter flow. This process is critical for the wind's feedback efficiency, determining how much of its energy is transferred to the galactic halo. Alongside turbulence, a family of hydrodynamical instabilities further sculpts the chaos. The Kelvin-Helmholtz instability occurs when two fluids slide past one another at different velocities, like wind over water. This creates the iconic wave-like rollers that break off into swirling vortices, which in a galactic wind can tear a cold cloud into brilliant, trailing streamers. Then there is the Rayleigh-Taylor instability, which acts when a heavy fluid sits on top of a light one. Gravity tries to flip them, but in the wind, the roles are played by pressure. Imagine a dense, cold cloud being accelerated by a hot, low-density wind. The interface between them becomes unstable, with fingers of the hot gas punching upward into the cloud while tendrils of the cold gas drip downward, a process beautifully described as cloud crushing. Supercomputer simulations bring this violence to life. They show a cold cloud entering a hot wind not as a solid bullet but as a melting iceberg. Instabilities immediately attack its surface, shredding it into a cometary tail of debris. The cloud is stretched, compressed, and torn apart in a matter of a few million years, a fleeting moment in cosmic time. The morphology of the entire outflow, whether it appears as a smooth halo or a collection of disjointed clumps, depends entirely on who wins this battle, the stabilizing force of the cloud's own gravity and pressure or the destructive fury of the instabilities. This microscopic chaos within the maelstrom has a macroscopic consequence, controlling how effectively a galaxy can rid itself of the very material that gives it life. Even with all we have uncovered, profound mysteries remain. The 24th clue lies in the anomalies, the stubborn pieces of the puzzle that refuse to fit. For every elegant simulation, there is an observation that defies expectation. One of the most perplexing is the mass loading factor, a measure of how much gas a wind carries compared to the rate of star formation. In many galaxies, this factor is staggeringly high, far beyond what our best models predict. The winds are simply too heavy, carrying away more mass than the known engines of starbursts or black holes should be capable of launching. It is as if a single rocket was somehow towing an entire mountain range into space. This suggests there are hidden entrainment processes at work, mechanisms where the fast-flowing wind grabs and drags along huge amounts of additional ambient gas from the galaxy, a cosmic snowball effect we do not yet fully understand. Then there are the ultra-fast outflows, detected as highly blue-shifted X-ray lines screaming from the vicinities of supermassive black holes. These are not mere million-mile-per-hour winds. These are relativistic torrents, moving at a significant fraction of the speed of light. Their origin is a deep puzzle. Are they driven purely by radiation pressure or by some more exotic process involving the black hole's spin and magnetic fields? How can they be so focused and so phenomenally powerful? Even our most sophisticated simulations struggle to replicate the detailed, multiphase structure we observe. The models might produce a hot, diffuse wind, but they fail to generate the long-lived, cold molecular clouds that our telescopes clearly see surviving the interstellar inferno. The physics that allows these delicate structures to form and persist within a maelstrom of hot plasma remains one of the great unsolved problems in astrophysics. These discrepancies are not failures, they are guideposts. They point directly to the frontiers of our knowledge, to the complex physics of turbulence, cosmic ray transport, and small-scale magnetic reconnection that we are only beginning to grasp. Each anomaly is a locked door, and behind it lies a deeper understanding of how the universe truly works. Our final clue points toward the horizon, where a new generation of observatories is being built to peer deeper into these cosmic gales than ever before. The James Webb Space Telescope is already transforming the field with its unparalleled infrared vision, allowing it to see directly through the dense dust that shrouds the birth of winds in galactic cores. It is showing us for the first time the precise moment a supermassive black hole's outburst begins to push against the galaxy's gas, watching the ignition of these storms in their infancy. But the next great leap will come from the Square Kilometre Array, a radio telescope network of staggering scale. When its thousands of antennas across 2 continents are linked together, it will act as a single dish with a collecting area of a square kilometre. This colossal ear will be able to map the cold molecular hydrogen in galactic winds with exquisite detail, tracing the full journey of star-forming fuel as it is ripped from its home. It will reveal the subtle magnetic fields that guide the outflow, showing us the invisible architecture of the hurricane. Meanwhile, proposed X-ray observatories like the Lynx concept are designed to see the faint, diffuse glow of the wind's hottest phase. Current X-ray telescopes give us a glimpse, but these new instruments will provide a high-definition movie, mapping the superheated plasma as it expands and interacts with the circumgalactic medium. They will measure the energy of ultra-fast outflows from black holes with a precision that could finally unlock their secret power source. Together, these tools represent a quantum leap in our perception. We will no longer be studying static snapshots of these outflows. We will be observing their dynamics in real time, watching how they change over millions of years. We will witness the life cycle of a galactic wind from its violent birth to its final dissipation, understanding not just its structure but its soul. This is the ultimate destination of our 25 clues, a future where the mystery of galactic winds is not just solved but experienced, as we finally learn to see the universe not as a collection of static islands, but as a breathing, living cosmos sculpted by the endless cycle of its own stormy breath. These 25 clues have illuminated a profound truth: that galactic winds are not a side effect of cosmic evolution, but one of its primary architects. From the first spectral fingerprints revealing their existence to the final frontiers of observation with next-generation telescopes, each clue has built upon the last, painting a complete portrait of a dynamic, breathing cosmos. We have seen how these winds are born from the titanic struggle between stellar creation and black hole destruction, how their multiphase structure and turbulent hearts defy simple explanation, and how their invisible partners from dark matter halos to magnetic fields guide their journey. They regulate star formation, enrich the vast intergalactic voids, sculpt galactic shapes, and even solve the mystery of the universe's missing matter. This is not a closed case, but an ongoing investigation where every answered question reveals new, deeper mysteries. The universe is not a static collection of islands, but a living, interconnected system, forever being reshaped by its own stormy breath. What cosmic force do you believe holds the next great clue? Share your thoughts on what shapes our universe in the comments below, and never stop looking up with